I'd say that Hopkins indeed promoted me in 2004. I think I promoted me last year. You know, I want to thank, first of all, Danny Dolev, that taught me how to unlock the door to the world, basically. And my partner in life, Michal, who carried me through that door. I'm going to talk about mostly technology today, but in the end, it's all about the people. Even though technology that I'm going to talk about is the process of how you invent it and how you take it to the real world, in the end, it's all about the people. And this is really the closed circle is here. And see how many people really invested in me and my crazy ideas to make it a reality over about a decade and a half. I don't have time to do justice. There's a story behind every name here, so I'm just going to say thank you to all of them, those that could be here and those that couldn't be here. They're all with me. I just want to mention that I had the big luck to have 3 waves of students that are listed here. And then my 4th wave is now picking up. But those 3 waves of students really is the reason for me to be here. So I bet my career on the internet. No, I didn't bet my career. I didn't care as much as that, whether I'm in academia or not in academia. I wanted to make that kind of impact. And these are the guys that actually did that. I didn't do that impact by myself, definitely. They did that, and I want to thank all of them. I had to pick one branch of work for today's talk. It's the branch I'm most passionate about. Maybe it's not the most academic only, but there is a lot of brain trust behind it. So according to our tradition in our lab, I have to mention that the first 2 parts of my talk today is really based on the work of Claudio Danilov, standing on the shoulders of Jonathan Stanton, who is here. And the last part of the talk, the 3rd part, is the work of my spread concept partner, John Schultz, and my lifetime colleague, John Lane. So let's start. So the internet is a big revolution. We all see it. I'm just going to focus on the technical side of it. It's a single network. There is one protocol suite that underlies all of it at the lower level, IP. And it's multi-purpose, so you can put many types of applications on it. And then each additional node that you add to it increases its reach and usefulness just like any other network. But in the internet case, each application domain it swallows greatly enhances the economic advantage of it. And because of that phenomenon, in the end, it's bound to swallow all networks. There's going to be only one, in my opinion. And this is something we know for a while. So, mail to email, phone system to voice over IP. I think majority of phone calls today are voice over IP, even if you don't know it. Fax to PDFs. Who sent fax lately? You scan it, you email it by PDF. Then it becomes IP. And started the process, and we'll talk a lot about that today. TV, the whole TV infrastructure is moving there. We'll try to help it faster than otherwise. Various control systems, the power grid, the water supply, all of those SCADA systems. Whether we want it or not, and we don't want it, right, the way the internet is today, but they are moving them nonetheless. So still to come, your cell phones. Today, the data is IP, but the talk is not. And there's not going to be a lot of time before the cell phone providers going to be just a pipe. So in this kind of world, how is it so successful? And I think it was so successful because of the art of design. The decisions, the paradigm, one paradigm that was selected early on. Today it looks obvious. At the time it didn't look that obvious based on people that were there and were speaking here in the past. Keep it simple in the middle and smart at the edge. Okay, that's how the internet is really built. In the middle, where you want to scale, you want a lot of traffic to pass, you have to be extremely simple. You need something, do it at the edge, end to end. So you do best effort in the middle. You may lose packets. You don't care who sent it, on what application, just move it to where it needs to go. And then at the edge, take care of it to be reliable, take care of it to be nice. Naming, CNN.com. What does it mean? You do it at the edge. When you come to the middle, you know where you go. And because of this paradigm, it would survive 4 decades and counting. My assessment is it didn't reach the midlife yet. It sustained at least 7 orders of magnitudes. I don't know too many systems that did that in the past. The other side is standardized, right? You want to be able to hook things, they work, but because of that, it's not going to change much as well. So, and that poses some problems because new applications come in. We built it for exchanges like email, and in the end, we want to use it for, interaction like we did with Danny, or TV that is flowing on it, and tomorrow remote surgery that goes through it. So it wasn't built for that. We want to, instead of point to point, we want to take it and distribute it to thousands, if not millions. We want a lot of people to collaborate in real time, faster than real-time file transfer. Danny objected to this. I also objected to it the first time I heard it. So what do you mean? I mean, we are real-time. How can you do faster than real-time? So, you have today a lot of data. And those data files are huge. It takes time to generate it. If you look at the TV flow at the pre-production level, it's huge. So if the TV program is 1 hour, to move the file of the internet takes 6-7 hours. You might as well FedEx it. Okay? So the people come to us and say, can you do faster than real time? What do you mean by that? Well, can you do it 6 minutes? Not 6 hours. The whole thing is 1 hour, that's faster than real time if you can do it in 6 minutes. People talk about how interactive you want to be. So you press it, you don't get a reaction within 150 milliseconds, you're not happy, okay, from the other side. Voice over IP, if we miss the 100 millisecond window, you don't feel that it really is interaction. If you talk about things that are delicate, like remote manipulation or remote surgery, the demand on the network is even below that. Because overall, you need to close the loop within 130 milliseconds, including everything. The robots, the control system. So the network has like 80, maybe. End-to-end dependability. We started with email. Okay, if the server is not there right now, in 5 minutes it will come up, maybe in an hour. We'll try for the next 4 days. Okay, that's internet dependability. Starting. Phone service dependability. You pick up the phone, you want it to work. Okay? TV service dependability. What do you mean by that? You look at your big screen, HD TV, the latest thing. If you see a speck, you're not happy. Okay? And in our case, these guys, you may not even see the spec, but the equipment is saying that something was not just right. You're not happy. This is TV dependability. To remote surgery dependability, when you have a life of a person on the line, right? So how do we bridge that gap? On the security side, we started from fault tolerance for email. We continue to secure financial transaction. But if our SCADA control system for our critical infrastructure, the power grid, is out there, this is not enough. Because if somebody compromises it, and we are not intrusion tolerant, we won't have power. So that will be interesting to see what we can do about it. So toward all those requirements, what can you do? And I think there are 4 things you can do, or 4 approaches that you can have. First approach, build specialized network just for that. Okay? We did that. How do you think we have today the ability to pass, in society, to pass tens of megabits per second per home in the US? You have 100,000 homes, 100 million homes, and each of them can get 10, 20 megabits per second at all time via the TV system, right? I mean, all TV today is digital, that's what you get. We built a specialized system for that. You put it to satellite, you bring it down to about 6,000 to 8,000 head ends, and then from there you go the last mile to the home. Okay? Or if you have a satellite service, you get it from the satellite. Was done in the past extremely expensive. Okay, each one of those satellites is like $300 million just there. You can build private networks. You can build a network just like the internet, but separate from it. So all you have on it is your traffic, and so you don't have the resource sharing problem. You don't have supposedly the bad guys on it, only the good guys, unless somebody connects it someplace and even grows the weed. And you still, it's still expensive. You need to build those private networks. They are still expensive. And you're confined to what IP can do. So if it's inherently not there, you're not going to get it doing private networks. The third approach is really the most common one people looked at in the last 15 years, to build a better internet. How do you do that? One way, you tinker with the current protocol. You improve it. Imagine you spend like 3 years into it, and you improve it by 1%. Are you happy or not? Look, it's 1% for a billion people. But it's 1%. I wasn't like excited about that. What does work in academia as a sales pitch is you say, clean slate design. Clean slate design, forget the internet, let's think about it from the ground up. We come up with new things, and then, great. The good guys would say, and then we will be the new internet. And then the smart guys would say, and then maybe we can learn something from it and incorporate to go back to improvement here. And then there are other crazy guys that say, maybe there is another way. That is maybe a hybrid between the two, which is to build overlay networks. And so that's what I picked. What is the overlay product? So really, it is in contrast to keep it simple in the middle and smart at the edge. You want to bring some of the intelligence and resources to the middle. And the only question is, okay, that's kind of trivial. I want to bring some of the intelligence to the middle, but how do you do it? Our way of doing it was taking software-based overlay routers, just software, regular programs, on regular computers, without changing anything. We're not doing smart things, just in terms of into the operating system or into the routers. Let them be. They know what they're doing, they'll improve it. We're just writing regular programs that run on regular computers that we put in some places in the middle, and we move everything through them. So if you're a networking guy and you look at that thing, you say, these guys are crazy, and it will never work, and I'm not going to let you publish anywhere. And if you want to get funding, you look for your friend somewhere else.